Hello students, welcome back. Let's continue our discussion on pipelining. In last session we have discussed few things related to the general meaning of pipelining. What is pipelining? We have taken example of laundry example, or I also discussed example of BTech program, how we are able to produce each batch at the end of fourth year. From fourth year onwards, how we are able to produce each batch of engineers every year. Okay, so you take an example, what is the benefit of pipeline, how it reduced the time to complete the entire all task and number of tasks, and why pipeline, that is the basic, ultimately the need for pipeline is to provide a parallel processing, to achieve a parallel processing. So it is a sub part, you can say it's a sub part of parallel processing. We discuss a few things related to parallel processing as well. Okay, so here processor with multiple functional unit, how we can divide our complete entire process into a number of functional units. So how we can divert the same operands or different operands to each functional unit in a parallel manner, so that we can have a parallel task. We have also discussed Flynn's taxonomy for parallel computers, right? So SISD, SIMD, MISD and MIMD. Okay, so we have covered these many things in last lecture. Now in today's session I will be focusing on mainly focus on pipeline processing. We'll be discussing on vector processing, on then there is a concept of array processor as well. So let's start our discussion with the pipeline processing. So what is pipeline processing? Pipeline is a technique of decomposing a sequential process into sub operations, with each sub operation being executed in a special dedicated segment that operates concurrently with all other segments. Okay, we have seen in the example of laundry as well. So the task, the complete process of laundry is divided into sub processes like washing, drying and folding, right? So each this task is performed independently by different segments. So on that segment we can consider that the first segment there is a washer who will wash the thing, and then in second segment there is a dryer, and then there is a table where one person will be there and he will be folding, right? So the complete process is divided into number of segments, and they have achieved the same way. It is also it is a technique of decomposing a sequential process into a sub operations. Okay, so at a time किस तरह से हमने देखा था कि पैरेलल पाइपलाइन मैनर में किस तरह से लॉन्ड्री का एग्जांपल हुआ था. Then a pipeline can be visualized as a collection of processing segments through which binary information flows. Okay, so it can be visualized as a collection of processing segments through which a binary information flows. Okay, we'll see how, in terms of, let's say it's a technical terms, so we'll see how our data is going to flow from one segment to another segment in a pipeline manner. So each segment performs partial processing dictated by the way the task is partitioned, right? Okay, so the result obtained from the computation in each segment is transferred to the next segment in the pipeline. Okay, so there is a segments, the complete process is divided into different segments. Each segment is responsible to perform some operation, okay, each having some combination circuitries and other operational units, so that they are going to perform something on and then they are going to store the result at the end of the first segment. The result will be transferred to the next segment as an input, and then the process is continuous. There will be a registers in between segments to provide isolation between each segments. Okay, the technique is efficient for those applications that need to repeat the same task many times with different sets of data. Okay, so this all other theory concept which we'll try to understand with the help of example, so we'll get a clarity in this. Now this is what an arithmetic expression that we are going to evaluate or we are going to perform in the pipeline manner. Okay, so this is the basic general example of pipelining. Now here in this case there is an what we call the expression that we are going to evaluate. Let's say AI into BI plus CI. So in this expression what we are going to do is we are going to perform addition as well as multiplication on the same data or on the group of data, right? So where I will be having AI, BI plus CI. So the same operation, one time we'll be performing as multiplication, and then we're going to perform addition on the value of I, which is ranging from 1 to 7, right? So AI into BI plus CI. So the same types of operation we are going to perform. Okay, so we can assume if we take in a sequential process how it takes, how we can do that thing, or if we introduce a pipeline. So see, this in this example we are going to perform this thing. So see, this is the complete segments. This complete process is divided into a number of segments. Let's assume that in this case there are 3 segments. Okay, so each segment performs something. Each segments having some registers. So there are in R1, R2, R3, R4 and R5, there are total 5 registers. Each segment will take input into a number of registers. At each clock pulse, the input will be transferred to the number of registers, and the same on the same register data, some of the operations, some combination circuits are there where some of the operations is going to be performed, right? So for evaluating this thing, to execute this complete program, right, to this thing, the entire the task is divided into a 3 segment. There are, let's say, 3 segments. In a first segment, we'll discuss this thing. It will be first segment. There will be input to the R1 and R2. In the first segment, there will be input to the R1 and R2. So A and B is going to be there in R1 and R2, and multiplication is going to be happen. So in the first segment, R1, R2 and multiply, right? These are divided into first segments. So what we'll be having is, during the first segments, the A is going to be loaded, B is going to be loaded into R2, right? Now in the second segment, the result of R3, the data will be there in the R3, which is a multiplication of R1 and R2. So it will be transferred. R1 into R2 is going to be transferred into R3. At the same time, CI is the third value, which is of C value, that will be transferred, will be provided as an input of R4, sorry, right? So at the same time, multiplication will be done, and the input of CR4 will be there in from the CI. And at the third segment, addition of these two will be performed. As R3. That is what this, the multiplication, this 2 multiplication of this number plus R4, which is CI, is going to be added, and the result is transferred to the R5. Okay, so this thing will be executed in a parallel manner, in a pipeline manner. Okay, so let's see how different things are achieved at each clock pulse. So this is what the content of registers in a pipeline. So here we have a clock pulses which ranges from 1 to 9. Okay, then there are 3 segments. The complete last example is divided into 3 segments. R1 and R2. At segment 1, it will take input to R1 and R2. At segment 2, it will give input to R3 and R4. So what will be the R3 value of R3? What will the value of R4? That will be where we've seen, right? And in segment 5, there will be a final result. Okay, so how actually the thing is happening? So at first clock pulse, okay, what will happen is, at first clock pulse, the first value of A and B will be there in R1 and R2. Okay, during the next clock pulse, when the clock pulse changes, this A1 and B1 is multiplied, and the result will be there in R3. At the same time, the first segment will receive input of A2 and B2. Are you getting right? Okay, so at second clock pulse, the A1 and AB1 is getting multiplied, and R4 is receiving value from the C1, right? And in third one, at the third clock pulse, the same will be, let's say the first, that is A1 and B1, whose multiplication is added with the C1, and at the same time A2 and B2 is getting the multiplication is actually happening. A2 and B2 is multiplying, and it is receiving C2, and at the same time A3 and B3, in segment 1 there is a new value of A3 and B3. So likewise, till the completion of task, everything is getting executed in segment by segment and in the pipeline manner. Okay, so the first data which is there, A1 and B2 is inputted in a segment 1, it is transferred to a segment 2, where multiplication will be there, and C1 value will be added, given to the R4, and then it will be forwarded to the segment 3, where segment 3 will add multiplication of R3, and will add R4. It will add, let's say, R3 plus R4, right? So this is how pipeline, in the pipeline manner, how the things are getting achieved. Actually this is a kind of arithmetic pipeline. We will be discussing arithmetic pipeline very soon. Okay, so general structure of 4-segment pipeline. Let's say we have a 4-segment. Assume that we have 4 segment in our actual part. So every task will be achieved with the 4 segments. Okay, so in segment 1 there will be some value. It will process, it will receive some value, it will having some operational units where some operation is going to be performed on the data, and the result of first segment is getting stored in R1. Okay, and the same result from R1 it is getting passed to as an input to the segment 2. Right? So likewise at the end of each segment there will be a register which will hold a result, a temporary result of each segment, right? So and each registers are connected with clock pulses. So at every clock pulses registers will receive a new value. Okay, now we will let's discuss example or space-time diagram or with the 4 tasks which is getting executed in 4 different segments. Okay, so this is what the general scenario where sequential manner, if we have let's say 4 tasks, our complete task is divided, the process is divided into number of tasks, let's say 4 tasks, and that 4 tasks are going to be executed in 4 different segments. Okay, so how it happens in a sequential manner and how it can be happen in a pipeline manner. We have discussed this thing in a previous example of laundry as well, but okay, so let's say T1, T2, T3 and T4, there are 4 tasks. Okay, there are 4 segment 1, 2, 3 and 4, right? So if this is what the scenario of non-pipeline architecture where each task are getting executed segment by segment. Okay, so T1 first will be T1 will be there in segment 1, yeah, at the second clock pulses. T2 will be there at the third pulse, T3 will be there, and T4 will be there. At the 5th clock pulse, T1 will go to the second segment. The same way 6th clock pulse, T2 will be go in the second segment, T3 will go in second segment, and T4 will go in second segment. At the 9th clock pulse, T1 will go into third segment for the further processing. The same 10th, T2, 11, T3 and T4, and at the 13th number of clock pulse, T1 will go at the last stage or last segment for execution, T2, T3, T4. So this is what the total time it takes to complete the entire T4 task, that is 16, let's say 16 clock pulses, right? So it's the same scenario can be executed in the pipeline manner where T1 will be there first time, T1 will be there into first segment. At the second clock pulse, T1 will there in a second segment and T2 will enter into a first segment. At the third clock pulse, T1 will go to the third segment, T2 will be there in the second segment, and T3 will enter into a first segment. At the 4th clock pulse, T1 will be there in the 4th one, T2 will be there in third, T3 will be there in a second segment, and T4 will enter into a first segment. So at the end of 4th segment we'll be having an actual output, right? So it will take 4 stages, 4 let's say clock pulses or clock cycles to full the pipeline. Once the pipeline is full, we'll be able to produce a result after each clock pulse, right? Okay, so it will take, for the first time it will take 4 clock cycles, and then after 4th one, at each clock cycle will be having a new result, right? So this is a 7, the clock total time it takes to execute a 4 task in a pipeline manner, it is 7, right? Now how this 16 and 7 is getting calculated, there is a formula on which all these things are getting calculated. So we'll be discussing on speed up how if we introduce a pipeline and then actually what is happening, right? So in this in this scenario, let's assume the one example how this this is 16, this 16 and 7 is getting calculated, how we calculate. So it's normal, but mathematically some equations are there, so let's try to understand that using that. So n is the number of tasks to be performed. Now consider in the case, let's say this is what a pipeline scenario, in the case of pipeline with k stages, that means k number of segments. In previous example we have 4 segments, right? So TP is the clock cycle time, right? tk is the time required to complete n number of tasks. N number of tasks, that means total time required to complete n number of tasks. There are let's say in this case, in this scenario, total time required in a pipeline manner is 7. How 7 is getting achieved? Okay, so is also it can be evaluated like time required to complete the first task plus time required to complete n minus 1 task, right? So number of tasks, that is 4, right? N minus 1, that is 3. Okay, now this is what the equations. Let's say time required to complete a first task, tk, time required to complete a first task, that is what, to complete a first task, how much clock cycles we need to complete the first task. So this is what the t1, to complete the t1 at here, it requires 4 clock cycles, right? So k will be 4 segments, right? So at the end of 4th segment there will be a result, right? So minimum to complete a one task, it requires k into tp, right? So k into tp plus n minus 1. What is n? N is the number of tasks to be performed. So we are supposed to perform a 4 tasks. So k plus n, it can be evaluated like kk plus n minus 1 into tp. That is what in this scenario k is what, 4. It is 4 segments. So one tp equal to clock cycle per time. So 4 into 1 we can say, that is 4 plus n minus 1. N is also 4, so n minus 1, that is 3. So k plus n minus 1, that is 4 plus 3, that is equivalent to 7. So it takes 7 clock pulses or clock cycles to complete the n number of tasks, right? The same way in a conventional machine, it is non-pipeline machine. That is what, how much time it takes to complete n task. That is tn equal to time to complete each task, n into tn equal to time to complete n task, right? So total time, so we can easily identify 4 into 4, right? N will be a 4 and tn will be a 4 time, right? For completing one task it requires a 4. So 4 into 4, it is 16, right? So speed up is getting calculated using this formula, like sk equal to n into tn, total n into tn divided by k plus n minus 1 into tp. Okay, so there will be one more example. We'll be having one more example of pipeline with the multiple functional unit. Okay, and multiple, not with the multiple functional unit, pipeline with multiple functional unit. Okay, so how a pipeline scenario will do work of multiple functional unit. Okay, so the same scenario we'll discuss. Now consider example, let's k equal to 4 z. We have 4 stage pipeline, right? So we'll be having 4 different segments. Now tp equal to t 20 nanosecond. tp is a time it takes to perform सब operation in each stage ना. एक segment के अंदर कितना time चलेगा, 20 nanoseconds. n equal to 100, so we are supposed to execute 100 tasks in a pipeline manner. Okay, now assuming that tn equal to k into tp, right? Total task in non-pipeline system is 4 into 20. 4 is what, 4 stages that we have, and 20 is the 20 nanosecond, which is the tp. tp equal to time it takes to perform some operations in each stage. So one task in non-pipeline system will take 4 into 20, that is 80 nanosecond, right? To complete 100 tasks, the pipeline system will take k plus n minus 1. This is what the formula that we have derived in a previous slide, k plus n minus 1, right? So what in this case, 4 plus n minus 1, that is we are supposed to execute 100 tasks, so n minus 1, that is what, 4 plus 99 task into 20. Each stage will take 20 nanosecond, right? So 4 plus 99 into 20 equal to 2060 nanoseconds. Okay, so to execute n, that is 100 tasks in a pipeline manner, it will take 2060 nanosecond, right? The same scenario, if we if you want to execute using a non-pipeline system, that requires n into k into tp, that is what, 100 into 80. What is what k into tp? That is to time it takes to complete in one task from the four stages. Okay, so 4 into 20, that is 80. So 100 into 80, that is 8000 nanoseconds. Okay, so this is what the difference. Now if you introduce a pipeline, if you don't have a pipeline, this is what is difference. Okay, so see the speed up is getting calculated is the non-pipeline system required time it takes to required in a non-pipeline divided by pipeline system it will take, right? So sk equal to 8000 divided by 2060, right? That is what 3.88. so this is what a speed up will calculate it based on this. And if we get this number 3.88, that is almost equivalent to 4, right? So a 4-stage pipeline is basically identical to the 4 identical functional unit. If we don't have a number of functional unit, but if we introduce a pipeline scenario in this theme, so 4-stage pipeline will do work of 4 different functional unit. उसका मतलब ये हुआ कि हमारे पास 4 functional unit है, उसके जैसा काम कर सकता है pipeline manner में भी, right? So we can achieve parallel processing like this in this manner as well. Okay, so in our normal systems, the computer in computer system, the pipeline structure is organized in 2 different ways: the arithmetic pipeline and instruction pipeline. So in today's video, we'll be discussing on arithmetic pipeline, and then next video we'll be discussing on instruction pipeline. Okay, so arithmetic pipeline, it divides an arithmetic operation into a sub operations for execution in the pipeline segments. Now arithmetic pipeline, let's take an example of arithmetic pipeline. Let's consider the example where no floating point addition of 2 numbers, right? So I think you guys are clear with the floating point addition, how we perform addition of 2 numbers, floating point numbers, right? Okay, so the floating point numbers come with this format. Let's say x equal to a into 2a, so and y equal to b into 2 raised to b, right? So a and b, these are the mantisas. Capital A and capital B are the mantisas, and small a and small b, these are the exponents, right? Okay, so our floating point number comes with this thing. Okay, we'll see the example, then you will get clarity of this, right? So if you want to execute this thing in a pipeline manner, this arithmetic expression in the pipeline manner, so it can be divided into number of sub operations and each sub operation will be executed in different segments. So let's assume that this will divide this complete process, the floating point addition process, into sub operations, and will be executing in 4 different segments. So how each segments will perform, or what are the sub operations that each segment will perform, are like this. Okay, so first we need to compare the exponent. Why? That we'll discuss, because if you want to perform addition or subtraction on floating point number, we need to compare the exponent, and if the exponents are there is a difference, we need to align the exponent. We need to align the mantissa to adjust the exponent, and then we need to perform addition, and then we'll normalize the thing. So there are 4 basic sub operations that we are going to perform in floating point adder. Okay, so this is what an example. Consider the following example where see, remember, compare the exponents, align the mantissa, subtract or add or subtract mantissas, and normalize the result. Okay, so consider the following 2 numbers. Okay, so in this case x and y, where 0.9504 is first mantissa into 10 raised to 3 is what? Exponent. The y equal to 0.8200 into 10 raised to 2. So there is a difference between exponent. Okay, so we need to first stage, during the first segment, what we are going to do is we need to compare the exponent by subtraction. So we'll be comparing this exponent, right? So subtraction, we'll subtract higher value, smaller value from the higher one. So 3 minus 2 will do this, and there is 1. Okay, so it is differentiated by 1. So there is a difference of 1. So we need to align these things, we need to adjust the exponent. Okay, so the larger exponent is chosen as an exponent of the result, right? So in this case, the larger exponent will be chosen as the exponent of the result. Okay, so 3 will be exponent of a result that will be chosen. In the first segment, it will simply compare the thing. In the second segment, we need to align the mantissa. Why? To equal the exponent value, we need to align the mantissa. So what we do is, there is a difference of 1 only, so will we perform only one right shift on y, because the value of exponent of y is lesser. Okay, so we need to make this value to 10 raised to 2 to 10 raised to 3. So to make this 10 raised to 2 to 3, what we do is we'll be simply performing a right shift on this. Okay, so this y value will be performing right shift, so we'll add 0 here, and 0 will perform shift here. Okay, so this is this entire mantissa will be shifted 1 bit to the right. Okay, and then the same, the exponent value is going to be increased, right? So 10 raised to 3, now it is equal. Now if these two are equal, then we'll be performing addition of this mantissa, right? So addition of mantissa, that is z equal to 1 point. This is why if you add 4 2 5 13 3 and 1 0 and 1, right? So this is what the result of segment 3. Okay, so in the segment 3 we'll be achieving this thing, and a segment 4 we need to perform a normalization. That means in a fraction number, if non-zero is there, so we need to make it to 0. So normalizing the result so that it has a fraction with a non-zero first digit. So this is done by shifting the, again the result is 1003. So if you want to make it 0, then 0.10, so we need to perform a shift. We'll be performing one more shift, that is 0.10324 into, will increase the exponent value by 1, 10 raised to 4. So this is the case. Okay, so each segments are performing how the entire floating point addition process is divided into a number of segments that we have seen here. So each segment, first segment will do what? It will compare the exponent, right, by subtracting the numbers. Then the second segment, it will align the mantissas, right, shift the mantissas, or so that the exponent value can be aligned, and then perform addition and then normalize the result. So the same can be viewed in from the flowchart point of view. This is what this arithmetic pipeline flowchart, where no, there will be an exponent a b and the mantissa a capital B. There will be this the operand will be there in number of different registers. R is the registers, so we know that at the end of each segment there is a register to hold the temporary result, right? Okay, so the entire process is divided into 4 tasks, sub operations, like compare, align, then subtraction or addition, and the normalize. Okay, so first thing, compare the exponent. In first segment we'll compare the exponent. If there is a difference, then there is a need of alignment, right? So after the comparison there will be a result here, comparison result, then difference, alignment. Okay, so alignment is that means what it will do, it will simply perform a right shift on the numbers, so that the mantissa can be aligned and the result will be there in the these registers, right? So second segment, what second segment do is, it will choose the exponent and align the mantissa. That means what, if in the previous case, that is 3 and 2 was there, so choose the exponent, that is what, the higher exponent will be chosen as the result exponent, and then we need to perform alignment on the mantissa for achieving or to make this exponent equal. And then segment 3 will perform addition or subtraction, the result will be there. And segment 4, there is, if it is a non-zero number, so if you want to normalize the result, then we need to perform that thing using by shifting one more to the right. So this is what the basic case. See, it is it requires some attention, it requires some readings of books as well to clearly understand it. So if you want to clearly understand the things, you can refer the reference book that we have shared with you. Okay, so there is a specific topic, so that you can get much clarity in these cases. Okay, so these are the some of the things which are very technical, so it requires some more components to properly explain, but I think it will help you. This will help you if you go through it, if you read the things, and then it will help you. Okay, so this is for today's session. We'll be discussing on instruction pipeline in the next session. Okay, thanks for the watching. Thank you.